So, welcome everyone to our third lecture on quantum topology without topology. Let's just jump right into it, right? Okay. Um, so today's lecture is basically about more graphical calculus in monoidal categories. So I will tell you something about kind of a generator and relation approach to monoidal categories, like one-dimensional cobordisms and in its various flavors as we have seen it. Um, So basically, how can we define those categories rigorously? Without topology, of course, because I'm not claiming they are topological objects, I'm claiming they are objects of diagrammatic algebra. So that's basically what I'm trying to explain today. And we will see, so those pictures. So this is basically kind of a Brouwer calculus thing. And I will define everything by generators and relations, and not topologically. That's kind of the point, right? I just like to simplify illustrations sometimes. You will see. Okay, the starting point for today is let's think about the decategorified story. Let's think about monoids, right? So the Grothendieck ring, as I explained last time, of a monoidal category is a monoid. Where does a product structure come from? Well, the product structure, so K0 of whatever monoidal category C is monoid. M and the tensor product basically decategorifies to the product in M. Um, and well, so let's try to see what's going on for monoids first. So there is a construction which you might have seen under the umbrella term of the whatever, the free whatever, the free vector space, the free group, the free whatever. And it basically means you don't impose anything except the relations you need to impose, namely the ones that makes whatever your outcome is, like a free group, what makes it a group. So the free monoid is kind of the easiest example you can imagine. So the free monoid generated by some set, let's say S, and I write generators and relations, and it's free. So free means I don't have any relations to worry about at all. It's the easiest possible construction ever. I'm just imposing exactly the relations to make it a monoid, and that's it. And in this case, it just means that my elements are just words in the symbols in some alphabet, let's say, words in some alphabet, and my alphabet is my underlying set S. And I call those things letters. Well, you could think of, for example, if S would be whatever, the set AB, then AB is good. Then anything you can concatenate from A and B would count as a word in some finite sense. What something like that. That's a word, and those are the elements of my free monoid. No rules at all. Just stack them together. Each word is its own element. The only condition it should be finite. Otherwise, we run into some problems. And this cannot be easier, right? You just pick an alphabet, and everything you can build out of this alphabet is a word. Everything you can build out of this alphabet is an element in your free monoid. There is some funny word, which I always tend to forget, but I wrote it down at least. So the empty word is a word, and it will be the unit in my monoid. So the empty word is also a word. I could also say, oh, I don't choose any letters at all. Okay. Right? I don't like to speak, so I just shut up and don't choose any letters at all. Yes, and how actually, the question is, how is this a monoid? How can I compose things? Well, because I allow everything, I just composition is just word times word is just word. Just just stack them next to each other. So whatever, AB times B is just ABB, right? And so on. So the easiest possible rule that that you can imagine. And the only relation you impose is kind of associativity, and that's nothing you really need to impose in this formulation. It kind of comes for free, but there's absolutely nothing you can do with a word. A word is a word, and there's no way to manipulate it. It's just what it is. That's why it's called free. Yes. So very easy concept. Free just means you impose as few relations as possible, just as many to make it whatever you want it to be, like a free monoid or a free group. For a free group, for example, you would impose that A has an inverse here in the notation here, and A times A inverse equals 1, because you want it to be a group. So you just impose exactly the relations you need to make it whatever kind of object you have in mind. In this case, it's just a monoid, and a monoid is, well, there's absolutely nothing. You have a unit, you have associativity, and that's everything. The unit comes for free, it's the empty word, and associativity comes for free in this description. It's just because you can concatenate words, and each word is well, there's nothing you can do. It's just what it is. Yes, so that's what I said. You have to be always a little bit careful with the terminology. The free monoid generated by S is just this bunch of words, and you can stack them together. There is also the free group generated by S. It's basically the same, but now you have also formal letters of the form S inverse, and you need to impose one relation. S times S inverse equals 1 times S inverse times S. So 1 is the unit, the empty word in your monoid. So that's what I would like to stress here. It depends. So freeness depends on as what kind of object you want it to be free. Do you want it to be free as a group? Do you want it to be free as a monoid? Do you want it to be free as whatever else you have in mind? Right. So let's give you an example, a very explicit example. So here, two very different examples. Okay. The free monoid generated by one object is just n. Why? Well, because, well, my object, I can just call it bullet. Okay. So all the words I can imagine are just bullet, 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 bullet. Let's say 4 times, and you can identify this as 4, of course. And concatenation of bullets resembles addition in n, of course, right? Because, well, whatever, 2 bullets and 3 bullets equals 5 bullets, and this is, of course, 2 plus, what is it, 3 equals 5, right? Nothing fancy. Yeah, so that's what it is. But in contrast, the free group generated by S is Z. Why is that? Because I now want it to be the free group in my alphabet. So I actually do have a bullet, and I also have a bullet inverse, which you, of course, then should identify with the same rules as above. You identify this as 1, and you identify this with -1. So you actually get Z. And again, it really depends. That already shows that it really depends on as what you want it to be free. A free group is not the same as a free monoid. A free monoid is usually smaller than a free group. You can also say something like the free commutative monoid. What does that mean? Well, you would impose one extra relation, namely, you would impose that for all letters in your alphabet, something like AB equals BC. And if you think about it a little bit, let's say your set S has 2 elements, bullet and star, then the free monoid is isomorphic to n squared. Why is that? Well, you can identify bullet with this element, let's say, and you can identify star with the opposite element, and yes, that's what it is. But the monoid generated by S is not isomorphic to n. It's a free monoid in 2 generators. Okay, so let me say it again. Being free is a relatively easy concept. You just allow all possible concatenations you could think of, um, and the only relations you impose are the relations to make it whatever kind of free thing you want. Do you want a group? Do you want a monoid? Do you want a commutative monoid? Do you want a commutative group? Whatever. Just impose exactly the relations to make this whatever the free commutative group on uh, five generators of on five letters. I'm sorry, not five letters, an alphabet of size five. Um, the question is, okay, that's an easy concept. So being free is always something very easy. You just can't make anything wrong. Whenever you have the question, do I need to rewrite this element? The answer is probably no, because you can't. It's free. The free monoid is the easiest example. That just any word is just what it is. For a free group, it could be a bit more complicated because you could have something like A inverse, B, for example, is not what it is. It's actually secretly just B because you because one of the axioms would be that you can cancel out A and A inverse. But okay, it's still pretty simple. And simple sometimes also means boring. So what you really want to do is you want to impose some relations. And relations just means you have um, I write R for relations, and this just means you have some word ABA. You can say this is BAB, for example. This would be a BAA. I could also say it's BAA, but I wanted to do BAB. This would be an example of a relation. Right? Strictly speaking, it's a subset of the cross product. So this is the left term, this is the right term, whatever. And I call them relations. And the monoid generated by S with relations are this funny thing is just a quotient by the quotient out by the relations. So meaning that two words are now equivalent if and only if you can obtain them by a finite number of moves from the set R. Right? Let's say I've imposed this one, then you would need to check whether two words are equivalent, whether you can obtain them by finitely many moves, well, moves of the form ABA equals BAB. And this is kind of a really important concept because usually monoids in real life, or monoids, groups, whatever, usually things in real life do not come by a generator and relations presentation. They come in some different flavor. I will give you an example in a second. Um, but having generators and relations is extremely powerful, as we will see, because, for instance, just checking that you have a map of monoids between two monoids, you just would need to, well, let's say you have a monoid of size 500, then you would first need to find a map assigning to each and every one of those 500 elements in your monoid um, a new element in the other monoid, and you need to check that all the compositions are, you need to work out all those multiplication tables. And no, generator and relation presentations are just extremely efficient ways to encode the multiplication table. To check whether I have a monoid map, all you need to do is to assign one element for each generator and check that the relations are satisfied, and yet automatically get a map of monoids. Same for groups, same for whatever kind of things you have in mind that you can give a generator relations description, like monoidal categories, as we will see later. And this is why this is extremely crucial. If you have a monoid in the wild that appears in real life, M, and you could find another monoid, uh, you could find S and R such that M is isomorphic to S and R. Um, and then we say that S and R give a generator relation presentation of M. And this is extremely important. We really want, in for almost all practical purposes, you really want to find this generator and relation presentation. Okay, so let me give you an example. You could do something like this. Same as before, I take my set to be one dot, okay? And I take my relations to be two dots equals one. Well, okay, that's my set of relations. And you would see that the free monoid actually is Z mod 2. Why? Well, because, okay, a dot, you have this element for sure, you have a dot, a bullet, and as soon as you write two bullets, you're actually back to where you started. So, and that's all you can do. Three bullets are then just, you can cross out two bullets, just with, again, one bullet, and so on. Right? So everything completely collapses, and it's Z mod 2. And you found the generator and relation presentation of Z mod 2, which is not that exciting because we're talking about Z mod 2, but you get the point. Um, uh, but the fun is this relation automatically imposes, so this one automatically imposes that your element bullet is invertible. So this is actually the same regardless whether you see it as being generated as a monoid or a group. So yeah, this could also help. Depends a bit. But anyway, the point is you found a generator and relation presentation of of Z mod 2. And it wasn't that hard. Um, and you could think of the symmetry group of the triangle. This would be kind of the dihedral group of order 6. Um, I just denoted by I2, 3, whatever. So 3 is a triangle. Um, I2 is kind of the classical notation. It is order 6. It's a symmetry group of the triangle. You have those two elements, A and B, and basically what you do is there are two ways to do it. So you have this ST presentation. So there are two presentations. So you can either mirror around this axis and call this S, and you can mirror around this axis and you call this T. And this gives you this presentation here. Ooh, this was bad. This gives you this presentation here because, well, I mirror around an axis that's certainly of order 2. So S squared equals 1, T squared equals 1. And you can check that actually that there is some kind of this relation, STS equals TST, this break type relation. There's another way of doing it. You could keep the same axis, like maybe I should keep it red. I just call it A, and it's still mirroring around this axis, and of course A squared equals 1. But B is now slightly different. B is a rotation action, and this is of order 3, of course. Whatever, B is this action. And this is of order 3, and you could check that those are the relations in the other presentation. So actually, there are now two different presentations of the same group, and that's what I mean. So this group arises in the wild. You would see it for the first time not by writing down some generators and relations. That doesn't make sense. You write down some random set S and some random relations R. God knows what you get. So don't do that. No, it arises in nature as a symmetry group of a triangle, and you kind of have two choices how to realize a symmetry group of the triangle, and both give you two presentations, and it's not directly obvious why they should be the same. So why should purple be the same as green? Well, it's not obvious, but they are actually the same. A slight difference here. So this one only really works if you want it to be as a group. This one is kind of the green one is kind of the monoid presentation. Again, those relations then imply that it's a group anyway, but it doesn't matter. So the point here is you have a group that arises in the wild, the symmetry group of a triangle, and you found the generator and relation presentation. And the generator and relation presentation won't be unique. Here are two different ones. So these are certainly different as generators and relations. The group they generate is the same. Okay, so we have found two different ones. So such a generator and relation presentation is by far is far away of being unique. It's usually not unique at all. And well, the point why this is interesting is this kind of triviality that every monoid, every group, everything basically has a generator relation presentation, and the proof is so ridiculously stupid. Um, it's good to know, but the proof is ridiculously stupid. You could maybe you could take just S to be this M itself, so any element is generator. Cool. And you impose the relations to be exactly the ones coming from multiplication in there. Yeah, that's a generator relation presentation. It's just a super useless one, right? The point of generators and relations is not that there exists one, that's good to know, but rather you find a very handy one. Like in this example, the group has order 6, but you only have 2 generators. So that's already much better. In this general lemma, I mean, the number of generators is the order of the group. I mean, that's not really helpful. And the relations are just the multiplication table itself. Yeah, okay. That's not really helpful. Right. It's I write here. It's of course useless. That's true. That's exactly true. And in general, it's just really hard. It's really hard to to find a generated relation presentation for your monoid. It's just a really hard question. But the point is, this other lemma, which basically holds by definition, just to define a morphism, if you have a generated relation presentation, to define a morphism, it's completely sufficient to specify your morphism on objects, on generators, and to check whether relations are preserved. And that's super useful. So this is super useful. Well, maybe I should say super, maybe I should just say useful. Right? I mean, this is really the point of generated relation presentation. In order to check something, you don't need to go through the whole multiplication table. You do it on your generators and relations. And if you have found a good presentation, like a small one, a slick one, then it saves you so much trouble. This is so good. So this is great. It's a triviality if you think about it. Everything is built such that it works. And the question is this hard question is: can you find a good generator and relation presentation for your monoid? And not, well, that's the main question. But this is something you should keep in mind. You only need to ever check anything on generators and relations. So again, instead of going through 6 elements and the multiplication table of order 6 times 6, you just have to check, you just have to find uh, 2 images for those 2 generators, and you just have to check 3 relations. It's much more efficient than going through 36 relations. Okay. Okay, this example is fun, but anyway. So if r equals 0, the only thing you ever need to do is only need to specify f of s, and whatever you do, it defines your morphism. So a free monoid always maps to everything, basically, because you never need to check anything. You can choose freely your elements, f of s. And the point is, of course, this was the decading story, right? And something similar should work for monoidal categories, and that's what I'm defining right now. And then we go through a lot of examples, and it's really easy. It's a really easy idea. It's a really slick and beautiful idea. And as soon as you see examples, everything will be clear. And I kind of do the same thing. Remember that on the level of object, a monoidal category is a monoid. So I just do the very same definition. Right? So I call my things object generators, and I would now write x tensor y tensor whatever z and so on. This is now I just write words in my objects, and I'm even very very lazy and just write x y z. So I just write words in my objects, and that's an object in my that's kind of an object that can generate. It's exactly the same story as before. Okay, and that's exactly what I call an object word. It's just, this is an object word, and it's just what it is. It's the same as for monoids. It's concatenation as for monoids. The empty thing is the monoid unit, and so on. A morphism word is defined exactly in the same way, but now you have two ways of decomposing things. Um, you can have your morphism here f, and you this was the wrong way around. So let me try again. This one here is, you have your morphism f that you've already generated, and you have a morphism g, and you can stack them together into a new morphism fg. Or you can have your predefined morphism f, and you do this recursively, and you have g, and you stack them together kind of in this way, and you have a new morphism f tensor g. So you can, so if you think about it, what on objects you kind of concatenate along the line, and on morphisms you can concatenate in this, or in this direction, and in this direction. And the idea is the same. You just have a certain predefined set of generators, the morphism generators, and you write words in these generators. Words just now means you have two-dimensional objects. You can write your words in a two-dimensional way. You can concatenate vertically, and you can concatenate horizontally. Yes, and that's what I indicate by those two symbols. Okay. And then you just define exactly what you think you would define, the free monoidal category, monoidally generated by S and T, and I would denote it by ST and, well, MT, because MT will be some relation set at one point. And the objects are exactly the words in S. The morphisms are the two-dimensional words, so one-dim words. Two-dim words. Oh, I can't write. And composition of words is concatenation horizontally, and for those guys you can concatenate vertically or horizontally. But as you know it from last time, you can stack things together in two directions. That's why a monoidal category is actually secretly a two-dimensional object. The unit is what it is. It's the empty thing in the monoid. You impose relations to mimic what you think should be true, right? So this looks a bit more complicated, but this is basically, this one here is the interchange law, which you need to impose, which is going this way and going this way. Is in concatenation is kind of the same. That's all there is to the interchange law. Yes. Let me do an example. And then we do more examples, which are much easier and completely obvious what I want to do. It will be all diagrammatic, so don't worry. So just take it for granted right now. So I don't have any morphisms. My morphism set, so this is T, my morphism set is 0. I don't have any relations, of course. My relation set R is 0 at the moment. And the only thing I have is my set S, my set of object generators. And this is, this Freemonoid is monoidal equivalent to vect over the natural numbers. Why? Well, because all objects are just dots. All morphisms are just identities, and yeah, there's just nothing you can do. And vect was this category where you have where the objects are just elements in your monoid, and the morphisms are trivial. So this is basically by definition. We will see much better examples in a second. Okay, and you can of course define relations same way as before, and you kill those relations in the monoidal category generated by S and T whose relations are. The only point to make is that the relations now R lives in morphisms, right? So I'm not imposing relations on objects. Objects are the wrong things to think about in category theory. I'm imposing relations on morphisms. Okay. Yeah. And same idea. If you have a monoidal category and can find S, T, and R, then we say you have generator and relation presentation of your monoidal category. And everything works as before. That's why I discussed it, and you could think about it. It's almost a tautology. Every monoid has every monoid. Yes, every monoidal category has a generator relation presentation, and the point will not be to write out the boring one where you just impose all possible combinations, but an interesting one. And to define a monoidal functor, all you need to do is you have to specify an object for all generators. You need to specify a morphism for all morphism generators, and you need to check the relations. And that's it. And this is super efficient again. Okay. But would be all very boring if I wouldn't give you a lot of nice, really nice examples. Okay. Okay. So I give you examples, and the only thing you need to keep in mind is that I'm getting very lazy. So I'm not writing x tens or x tens or x tens or x. I just write x to the k because that's really what's a tensor product is multiplication. That's really what's going on. Okay. So here we go. My favorite first example is a category of symmetric groups. How does it work? Okay, I have S. My generating set S is just a bullet. So all objects are just a certain number of bullets. Here you go. Let's say 5 bullets, another 5 bullets, whatever. And the only generator I have, so by the way, I should say identities are by definition included. So I don't need to write them down as generator. So I also have those diagrams, just to be sure, from dot to dot, the identity. They're not included because in the set T, because you never need to include they are included in the definition, not in T. So the only non-trivial thing I can do is I can cross two lines. Okay, I can whatever. Um, I can cross two lines, something like this would be, and I can do this one. Let me explain how I get there, and I can do this one, and maybe this one, whatever. Okay, so let me explain how I get there. Well, I secretly have cut my diagram into, let's see, 4 pieces probably. Here you go. And each piece, so let's analyze this piece here. So this secretly is this one. So this is this one, and secretly it's actually the horizontal concatenation of the generator with a lot of identities, which is completely allowed. Okay, so I used here in each of those slices, I used horizontal concatenation, and in the time direction, I used vertical. It's vertical direction, I used vertical composition. In the horizontal direction, I used horizontal composition. And all I'm saying is that all diagrams you can stack together from this principle. Those are allowed diagrams. So everything you can stack together from those ideas. And the set of relations I would impose are the relations that you see in the symmetric group, right? So this is invertible. And this is what, I mean, this is called the Reidemeister move. We will see more about it later, but it certainly holds in the symmetric group if you think about it as a permutation, right? So this element stays where it is. And if you just think of it as a permutation, then it shouldn't matter how I draw my diagrams. And this is exactly what's going on here. So this is exactly the same permutation. So I impose it there the same. And the magic, the real magic about this generator and relation presentation is that this is all you need to impose. So here's, by the way, the same. Of course, they are the same permutation. Oopala, as you can see. The point is that just having those two relations immediately implies that all kind of ways to draw a permutation in this sense gives the same answer, which is not trivial and a bit surprising, but anyway. And you get the category of symmetric groups. That's why it's called the category of symmetric groups, because in each home space you have a symmetric group. Okay. We'll see more examples like this. So before I move on, or before I repeat what I just said for this example, so here's my set T. Let me just say that there is also this relation, but you don't need to impose it. It's a special case of the interchange law. I leave it to you to check that, to click on 2.8 and see that this is really a special case of the interchange law, which I automatically want to have satisfied in my category generated by something, because that's what I do. It should be a category generated as a monoidal category. So I impose all the axioms of a monoidal category, maybe more relations. So I don't need to impose this is already contained in, it would already hold in the kind of the free symmetric, the free category generated by S and T. Okay. And okay, it's a non-trivial fact that sym is actually isomorphic to some kind of topological version of sum, which is kind of a full subcategory, certainly not a full subcategory, a subcategory of one-dimensional cobordisms. And this just means that this algebraic description is a very slick and combinatorial algebraic construction of this category sum top. And this is not quite obvious, because it kind of means that so sum top would be I could draw any diagram I want to draw, something like this. And kind of what I need to do is I need to cut this. Well, let's say I cut it here. This is a bit trickier. I cut it here, and then I cut it here. I kind of cut it generically to cut out all the crossings. This was a really bad cut. And then I see that this is actually generated by, well, this was a bad example, but this is kind of generated by pictures that are more rigid, because this is kind of a rigid description. This is a topological description. There's a same, and the rigid description, that's kind of the kind of statement here. There's a same. So you can draw your pictures as you want, and they will always do the right thing, but you never need to check anything more than, well, you need to assign, you never need to check anything more than you need to assign an object to S, and you need to assign a morphism to T, and you need to check that those relations are satisfied. And then you have already constructed the monoidal functor, which is, if you think about it, this is just a ridiculously slick description of all symmetric groups of those cobordisms at once. And I think that's pretty amazing. It's really, really easy. So let me repeat it. So S is just one object. So S just has one element. So all objects are just words in this element. So just dots, finite number of dots. There's only one non-trivial, so there's only one non-identity isomorphism. There's only one non-identity element in my set T. So all diagrams are kind of concatenations of things like this. You can concatenate it vertically, whatever, with this to get, what is it? Whatever. I hope that was right. Or you can compose it horizontally by stacking something on top, And that's it. So this is how you build all your morphisms, and you only need two relations, which are usually called the Reidemeister relations. Well, there are two of them, and that's it. And it's just extremely. You just described all symmetric groups in one line, basically. And at the same time, some topological category of one-dimensional cobordisms. This is just amazing. I don't know how you feel. I think this is pretty amazing. Um, yes. So let's try to describe the whole category, or well, not yet. Another monoidal subcategory. This will be the whole category. Another monoidal subcategory. The idea is the same. You just have dots, and now you have two morphisms, and you have one relation which should look very topological in nature. And maybe let me run you through this relation. How does it look like actually? Okay, let's say this side. What you should think is like here it's cut, and the bottom part is this tensor, this, and the top part is this tensor, this. Okay, and you get a category of diagrams of the form. Well, you have a certain number of dots at the bottom, you have a certain number of dots at the top, and you can do something like this, for example. And it's usually called something like the Temperley Leap category. Also, it goes actually back to those three guys. So I sometimes also call it the Rumatella category. Um, it's pretty easy. You just have a certain number of dots at the bottom, you have a certain number of dots at the top, and you connect them in all crossing less ways. You don't have any crossings, but everything else is basically fine under the non-trivial but identification with of this very slick description as a monoidal subcategory of cobotisms. So this just means, well, this relation implies basically all isotopies you can think of. Okay, it's again a very slick description of something that is definitely non-trivial. Um, the Brouwer category, BR, is now the description um, is now my generated relation description of one-dimensional cobotisms, which I actually state in the theorem itself, but I don't prove it because this is a topological fact that we are doing something without topology. So kind of, I will always work with Brouwer, but you should always think I'm using one-dimensional cobotisms. And how does it work? Well, generating set is still the same. Generating morphisms is a combination of the other two. So now I can draw all diagrams which have some height points or cross. And there's a certain set of relations, which I don't want to go too much into details, but kind of all kind of very natural relations, like this one here, right? It's just saying that this guy is the same. So this last relation here is just saying that this guy is the same as this guy, which certainly should be true in any kind of topological interpretation. So this just means now your words are just things you can draw from those generators, whatever, something like this. Yeah, whatever, something like this. Maybe with another cup here, whatever. Would be a morphism from 1, 2, 3, 4, 5, 6 dots. Sorry, I read from bottom to top, from 4 dots to 6 dots. All right. And of course, now it's totally trivial to define the functors from sum to br by just sending exactly the pictures to the pictures, because observe these relations are imposed in Brouwer as well, and this relation is also imposed in Brouwer as well. So you get for free those monoidal functors, and actually they are faithful. Okay, but the point is, this is the point. This is a generated relation description of one-dimensional cobotisms, and a very slick one. It's not so bad, right? I mean, it's really not so bad. You have just one object. You have three morphism generators, so just one object generator, I'm sorry. Three morphism generators, and how many relations? 1, 2, 3, 4, 5, 6, 7, 8 relations. That's not that bad, actually. And all other isotopies you could think about just follow from those relations. That's that's pretty good. I think that's pretty good. I think that's pretty good. And the point is, um, the left diagrams here, also they look exactly the same. One of them is just an algebraic notation, algebra, the left side, that's Brouwer. And one of them is actually a topological object, the right side. That's one cop. And the point is, I replaced some topology with algebra here. So that's kind of the point. I'm never telling you anything about topology. I can do now everything I want, everything kind of I want to study about one cop. I could do it in Brouwer, which is the algebraic way of doing it. Okay, I kind of sketched the proof. You can have a look at it. It's not, well, it's not so bad. You basically need to find some Morse positioning of cobordisms. You slice it into pieces, and each piece corresponds to one of the generators of the Brouwer category, which shows that the functor is full. Showing that the functor is well defined is easy because, of course, those relations hold in one-dimensional cobordisms. And the only complicated thing is that it's faithful. This is painful, and I just don't want to do it. So basically, you basically need to find a normal form for one-dimensional cobordisms. Anyway, the other way around is hard because you don't have a generated relation presentation of one-dimensional cobordisms. There is some inverse functor by the theorem, but of course it's exactly doing what you think it is. But to check that it is well defined is exactly basically D, because you kind of need to check that all relations hold in Brouwer, but you don't know the relations for one cop. So Brouwer is easier. So in some sense, this is I kind of claim here this is easier, because you precisely know what kind of relations hold. Yeah. So let me run you through this once more. You have this algebraic description of one-dimensional cobordisms, which is really handy. You only have a certain number of relations. You have a very small number of generators. It's very slick, and it's kind of much more handleable than one-dimensional cobordisms themselves. And now you found a way to algebraically study one-dimensional cobordisms, basically. Okay, and of course, there are now many variations of Brouwer, which I'm going to discuss in a second, because as we have seen in the last two lectures, there are many variations of one cop. So Brouwer should have many variations as well. I just go through it very quickly, and you just have to look at it and think about it. It's basically the same example. Oh, there are various versions, and that gives them various names. There's a quantum Brouwer category, there's an oriented Brouwer category, there's an oriented quantum Brouwer category. And basically what this means is oriented, you put in orientations. Strictly speaking, to make this work, you need an extra new element, an object generator, which keeps track of the orientations, like from star to star, I have a diagram that looks like this, points down, and from object to object, I have a diagram that points up. But that's not hard. It's just a pain in the neck to keep track on it. And the quantum means that I kind of allow now pictures like this, overcrossing and undercrossing pictures as new generators. The example would be quantum sum, that was this category here, where I would draw now pictures of the form, where's quantum sum of the form, like something like this, for example. And this is actually the category of braids. Right? So now I've over and under crossing the category of braids. And whatever, you have the analogs of the theorem. All the difficulties actually in this theorem already. If you know, then to prove something like this isn't all that bad anymore. So if you allow over and under crossings, then quantum Brouwer, Q Brouwer, is an algebraic description, an algebraic model of tangles. Right? Just keep in mind that there are certain adjectives or whatever. This is that you can attach to Brouwer. Oriented means oriented. Quantum means I have crossings. That's it. And you can attach it to temporally to TL or to sim as well. right? You can have an oriented version of OASIT or an oriented version of TL if you want to. No problem. Okay, I'm almost done. I show you something slick at the end. So let me repeat whatever we have seen. I showed you a very, very slick way of defining certain categories, namely by generators and relations, like this, the categories of symmetric, modeled on generators and relations for monoids, the category of symmetric groups, a slick presentation of all symmetric groups at once, categories of cobordisms, Bauer category, it's kind of the Bauer version of categories, whatever. And it's super helpful to have those. We will see this. This will be the whole flavor of kind of this lecture series. We'll see this in action several times. It's extremely important. I mean, it's a very simple and still extremely important idea that you kind of replace something that you like by a more handleable generator and relation presentation. Okay, but now comes a slight cut here. I want to define something different, or I want to discuss something different, which is still diagrammatic in nature, so don't worry. But it's slightly different than what we've seen before. I want to tell you what algebras and monoidal categories are. And this should generalize the notion of an algebra. Okay, that's exactly the point. I want to generalize the notion of an algebra. Okay. And an algebra in a monoidal category is nothing else than, well, what was an algebra? An algebra was something way of a multiplication. And a little bit of bad terminology, it should be more like a monoid in a monoidal category. But anyway, the standard terminology, I think, in quantum topology would be an algebra. Anyway, and if you think about it, what it is, it has a multiplication and it has a unit. And just now do everything in your category. So an algebra in a monoidal category is just, and I read just A, but actually it's a triple of an object, okay? A multiplication morphism from A tensor A to A, it's just a morphism, and a unit morphism from the monoidal unit to A. Such that, well, what would you do? Well, for an algebra, you would write something like A, B, C should be A, B, C. And in the diagram, it looks exactly like this. So this is a associativity diagram. So A and A bracketing this way and going around, and bracketing the other way and going around are the same. This is just exactly this thing here. And you would write unitality, which is just something like this, equals A, of course, or the other way around. And those are, let's see whether I get those correct. Yes, those are those two diagrams. It's just saying, yeah, if you, it's exactly what you think it is. I mean, it's the unitality. So this is associativity, the associativity constraint, and this is here the unitality constraint. And the only thing I did is I wrote everything in terms of commuting diagrams. There's no secret whatsoever. Yeah, so this is a pretty harmless definition. We'll see some examples in a second. The only thing I should mention here so those guys should remind you that I'm actually not working in a strict setup. So this is kind of a non-strict thing. So in a strict setup, those diagrams are even simpler. So this is associator, and these are the unitors. That doesn't matter. That doesn't matter so much. In a strict setup, for example, the whole diagram upstairs would collapse to this being the identity here. So this would be the identity in the strict setup. Okay, so an algebra is an object together with a multiplication morphism, such that the obvious diagrams commute, namely the ones that mimic associativity and unitality. Don't worry, I will draw diagrams in a second. It makes it much clearer. But of course, there's also the notion of co-algebra, which is exactly, well, I should learn drawing, which is exactly the same, but with all arrows reversed. So a co-algebra would have a co-multiplication map from A to A tensor A. Okay. Don't worry, if you see pictures, everything will be clear. And I will do the following. So write down pictures for all things. Okay. So I will encode my multiplication in this picture, in this merge picture. It merges in kind of, I think of it as I have an element in A, just analogy, right? I don't have any elements, but I have an element in B, and it's this merging spits out the element AB. Right? That's my multiplication merge. Um, the unit is this object, and the unit is this morphism. It's like the starting dot. It goes from nothing, which is the monoidal unit, to my A. Right? It basically assigns nothing. It just basically spits out A. And a co-algebra is, it sounds complicated because we are all biased. We all like algebras because we've grown up with algebras. But a co-algebra in this setup is nothing else than, well, why should I read why should I read from bottom to top or not from top to bottom? The co-algebra is exactly the opposite way around. So the co-multiplication is a split, and the co-unit is a dot morphism. And and this is again, of course, in the strict setup, because whenever I draw diagrams, it's strict, right? But it doesn't matter so much, as we have seen last time. And associativity is just this relation, and unitality is just this relation. Yeah? So this is asso, and this is unit. It's kind of a fun calculus. So I shouldn't have done that. So it's asso and unit. So you can draw your diagrams like whatever and stack those things together in the same way as before, like horizontally, vertically, right? That's the point of this graphical calculus. And the relations you impose are exactly those ones. And whenever you have some morphisms in your category satisfying these relations, then you have found an algebra or co-algebra or whatever in your category. Oh, this is actually the co-unit. I'm sorry. Whatever. Doesn't matter so much because I'm using those diagrams, right? Anyway. Yeah, so can we see this in any monoidal category? The empty diagram has a structure of a co-algebra. Yeah, okay. Here's the multiplication for the empty diagram. It should go from empty tensor empty to empty, and here's the the unit for the empty diagram. So this is kind of a boring example. Anyway, this one is fun. Yeah, it's in Brauer. You'll see it. But so this one is kind of a trivial example. The unit always is an algebra object or co-algebra object. An algebra. Of course, we want to generalize things. So algebras and co-algebras and sets are just monoids, basically, co-monoids, whatever. And in fact, there would be algebras in the classical sense and co-algebras in the classical sense over your chosen ground field. Think about it a little bit. It's not so hard. I just used exactly the same definition, basically, just in a categorical setup. Funny example in Brauer, this guy, two dots, that's actually an algebra object in Brauer. How can we see this? Well, so we need a unit. The unit should go from empty to two dots. And here you go. There's a diagram from empty to two dots. And you would need a multiplication that should go from two dots, tensor two dots to two dots. And here you go. There's a multiplication map. It's kind of this pair of pen thing, if you want to think about it like being closed. And well, here you go. Here you check associativity and co-associativity. Right? So this is Cut it like this and you will see it. Not co-associativity, associativity and unitality. Cut it like this and you will see it. That's exactly associativity and that's exactly unitality. And they're topologically absolutely clear. You just pull in the slack, and that's the cobordism, as I explained before anyway. And of course, by just mirroring those diagrams, right? It's also a co-algebra. And co-algebra is really just mirroring everything. That's why, I mean, I said again, it's kind of weird. We are all used to algebras from basically the very start, like multiplying numbers and so on, but actually co-algebras play absolutely the dual role, and there's no way to diss them. To right, they are digit S algebras, and yeah, they're actually the same, just a matter of convention. But we still don't like them so much. Life is complicated. And the Frobenius algebra is, and this is a really fun example. A Frobenius algebra is well, in C again, of course, in C, Frobenius algebra in C is an algebra and the co-algebra. So I have diagrams of both directions such that this relation is satisfied. That's a funny relation. You will see it. Well, you will see it in action. So yeah, so this is a funny relation. We will see it in action several times. But you basically can think of like this is a relation that actually holds among cobordisms. Like, let's take this picture. All that it's saying is if you do something like this, I will explain the picture later, but if you do something like this, and you should think of this as being hollow, so I can walk inside those hollow things. Whoop, whoop, whoop. And this is the same as in the middle, you see this diagram. And if you just think about it topologically as surfaces, because they're hollow, then yeah, that's a true equation. And the point of Frobenius algebras is kind of that's all you need in order to describe these topological objects, the surfaces. Again, this will be an algebraic way to describe topology, basically. But for now, you don't need to understand this. For now, you don't need to know this. Just a Frobenius algebra is an algebra and a co-algebra with this extra axiom, the Frobenius axiom. And of course, I mean, if you've seen Frobenius algebras before, that in fact, Frobenius algebras are exactly Frobenius algebras. And in Frobenius algebras, you already see some nice topology going on, because you can define a cup, define it to be the composition of this one, the product, and the co-unit. You can't do this in algebras and co-algebras. You need both structures, right? So this is M, and this is the co-unit. So this one, which I called E. And of course, the opposite way around, you can define a cap as a co-multiplication flanked by the D and the unit I. And then just this is an exercise is to prove that now we get all those topological relations, for example. For example, those ones here. Like zigzag, and you could pull things around and everything. So this is, again, that's the point, right? We're doing topology here. Secretly, we're doing topology. So all topological relations you can think of basically hold in Frobenius algebras. Okay, and yes, everything here is strict, but we don't worry about that too much. Okay, last notion for today. So whenever you have algebras, whenever you have monoids, you should think they act on. Groups act on vector spaces. You could define groups and categories. Algebras act on vector spaces. So algebras and categories should act on modules and categories. So what could this be? Well, here's the formal definition. I will draw a diagram in a second, but basically as usual, right? I will always draw diagrams. Basically, it's an object together with an action. Okay. And in this case, it's a right action. You will see it in my diagrams below, such that the usual diagrams commute. So usual. So some kind of associativity and some kind of unit. Really, what do you think it should be? Okay. And you can also define an equivariant morphism. Don't worry about it too much. I'll show you just the pictures. So what is now? So okay. I will encode the action map as follows. So I have now an object M, and this is a module I want to act on, and it's slightly different than the algebra because I don't have anything like M to M. So this doesn't exist. Okay, this maybe I should try it again. So I don't have any map from my dotted M. I don't have anything like this, right? Module is a weaker notion. I just don't have anything like this. Okay, but I have my action is just sticking my algebra to my module. My module is a dotted line. My algebra is a solid line, and the things I pose are exactly associativity and unitality, and intertwiner, an equivariant map is just you can slide the action through. That's it. So now it's exactly the same calculus as before. You just have now a fixed line, which you can't move anymore. That's why you also have right here, because A comes from the right. That's why it's right. M is fixed. You don't move M. That's what makes it a module and not an algebra. And M is fixed. Yeah. And of course, there's a version from the left by just doing everything from the left, but let's not worry about that. Let me give you a topological proof that composition of equivariant morphism, diagrammatic proof that compositions of equivariant morphisms is actually equivariant. And here you go. It's pretty easy. So F and G are equivariant, so F is equivariant, so I can pull this lag up. G is equivariant, so I can pull this lag up. So FG is equivariant because now I can pull it up and down. And that was a ridiculously easy proof. And now try to verify that using the definitions, and it gets a bit, well, it's not hard, but I mean, this is just an easy, super easy proof. The examples you keep in mind are, of course, the category of right A modules is now a category because I just showed that compositions of equivariant maps are equivariant. So those are the morphisms, and the objects are just M. And if I stack M together with M, then yeah. Well, sorry. If I stack two morphisms together, then you get a new equivariant morphism. So this just checks out by the following lemma. And of course, everything is built to generalize the classical notions of algebras and modules. Otherwise, it would be boring, right? That's why we do this stuff. Let me just give you another diagrammatic proof. And there's some, the exercise this time is like verify diagrammatically that whatever holds, something like that. That's actually a lot of fun. So let me give you another diagrammatic proof of a well-known fact. Let's say in vector spaces is a well-known fact, which is a bit painful to write down. The diagrammatic proof is easy. I call it a proposition. So if you have a Frobenius algebra, then every right A module is also actually a co-module. What is an A co-module? You can think about it, what it is, right? You just turn your pictures upside down, and that's it. How do we do this? Well, here's the proof. This is already done. So we're already almost done. The proof is I define my co-action by using my action. So here you go. So here's my M. And I want to define this thing. And what I do is the following. I only know how to define this thing because that's where I started. And I just use the map from before to pull it up. And right, everything is built topologically. So I just use this picture as a shorthand for this one. strictly speaking, it's just a shorthand, right? But of course, I just want to pull it up and I'm done. And you verify that the axioms are satisfied. And it's really simple. You just play games like this. So associativity, this is equal to, well, draw it as it should be, do the associativity downstairs and pull everything straight. And that's it. It's not very hard. Um, and well, and vice versa. How can you show it vice versa? By just, well, turning the pictures upside down and you're done. Yes, so I would really recommend to do some of the exercises as usual, um, and otherwise, so so this is, for example, fun. And yeah, well, otherwise that's what is for today. So let me repeat what we have seen today. A lot of diagrammatic calculus. I hope it was fun. Like first, what is the notion of being generated by something in this monoidal context, motivated from what we have seen for monoids, and then a lot of kind of diagrammatic nonsense regarding algebras, co-algebras, modules of algebras, which in diagrammatic pictures is really not scary at all. It's exactly what you think you should do. Like, yeah, well, this is a co-action, and the co-action just looks like a co-multiplication with one fixed strand, and so on and so on. So a module in this setup is, well, in general, it's nothing fancy. It's just the algebra itself, basically. But now you're not allowed to move a certain thing anymore. So that's what's going on here. That's all there is to it. And next time we will do even more diagrammatic calculus. But for today, I would just say thank you very much for listening. I hope you enjoyed it, and I see you next time.